I think it's just the breadth of topics that they have here. It's like the smallest things that C++ offers us to like the broad eagle eye view on like architecture, software architecture, and other topics as well. So it makes it unique in that sense.
So thank you everybody for showing up. I've got a lot of material to go through and we just lost quite a bit of time, so we'll go a bit fast. This is a continuation talk from my talk at CppCon last year. Last year I introduced work contracts, which is a concurrency architecture that I designed for extremely low latency systems. That talk focused on why we should use things like work contracts. It displayed the performance and sort of the underlying algorithms. This year I'm coming back to show you how to use work contracts, not why to use work contracts. So this will be less technically deep, less mathematical, and more code and more how to use the system. So about myself, my name is Michael Maniscalco. I work for Lime Trading. We develop software for market data and for trading in high frequency environments. My specialty is working in the market data on low latency for the market data. At heart, I'm an algorithms guy. I've been messing around with things like data compression and whatnot my whole life. We'll skip through all that stuff. I have a couple of different GitHub repos for different things. Building CPP is for professional grade code using C++ 20 and above. And then my personal website, which is older, which has a whole bunch of stuff that no one's going to care about. And that's what my daughter thinks I look like. One of them anyways. I'll skip through these. People can come back and look if they're interested. Now, with work contracts, it's a very low level system. It's almost a primitive on its own. And that is by design. So this is a very simple system. There's no bells and whistles. It is just the lean, smallest part you can get into a concurrency library. And the idea is that it does plenty on its own, but you could build on top of it. So it forces no design onto you that isn't utterly necessary for concurrency. As simple as possible. So I already started the recap on the CppCon 20. The secret sauce under the whole system is signal trees. So the way work contracts works is it does away with queues completely, because queues don't scale well. No matter what you do with them, you add more threads. Eventually, the contention on the atomics will degrade the performance, and throwing more CPUs at the problem does not scale. So work contracts is built on a signal tree structure, which is a lock-free structure that does not have any kind of ordering to tasks. Instead, it associates a signal with each task in the structure, and the scheduler can find those signals associated with the correct task and execute it. And by doing this, we eliminate all the contention that goes with queues, and we wind up with 40 to 100 times faster than the fastest concurrency queues used in other task-based systems. These are a couple of the benchmarks that we showed last year. So under medium contention against other solutions that use multi-producer, multi-consumer queues, lock-free queues, most of the systems behave pretty much the same, but the green line is work contracts, and it continues to go up and to the right, which is what we want, no matter how many cores we throw at it. And that difference becomes much more distinct as the contention increases. So this is the most demanding benchmark with the smallest, tiniest little tasks. And all of the queues you can see at the bottom, they just kind of collapse. They don't flourish under that kind of contention. But work contracts with signal trees scaled to the number of cores. And that is the basis for work contracts, is this particular engine. So why does this shine? Where do you want to use it? Anywhere where you need deterministic latency. So these are small tasks to carry information very quickly. And in a lot of environments, data that's even a couple of milliseconds old is useless. You want data that you can rely on now, that you can trust that it's timely. Those kinds of environments, this system will thrive. I just showed you that it has linear scalability, so you throw more cores at it, and it does more, it can operate on more concurrency at the same time. The signal tree itself is amazingly good at fair scheduling. So as a scheduler, it has no infrastructure whatsoever specifically to make it fair. It has no ordering. As I said, there's no LIFO, FIFO, no queues. The signal tree itself is just incredibly fair, and so by its own design, it will not let tasks starve. Every task that is scheduled will get a run without any extra effort and no synchronization. So mapping things out. We generally know how these kinds of things work. You can break down your concurrency into 3 areas. You've got your thread pools, you've got your scheduler, and you've got your tasks. In the work contract system, there is no thread pool. This is something you have to bring yourself. It is by design. So that's on purpose, and we'll discover why as the talk continues. The scheduler is called a work contract group, and this is where the signal tree resides. And basically, this is just a scheduler, so it does nothing except scheduling. It doesn't bring any threads, it doesn't bring any kind of thread pools or anything to the game. It's just a scheduler. And work contracts are basically the tasks. Now, work contracts aren't directly tasks. They are intended to be long-lived tasks, and they can carry state with them, and they can be repeatedly invoked and scheduled, and they have a asynchronous structure to them, so they go beyond a task. And they're meant more to encapsulate logic, not a one-shot task with data in it. It's logic, then you can bring the data in to that task through whatever you capture in your lambda or functor or whatever that you used for your task. So that is work contracts. Work contracts have a state. When you create a work contract, there's 3 possible states. Idle, which is you're not scheduled for execution. And when you schedule, you'll go to the work scheduled state, which is in the center. And at the end, when you decide you no longer need this contract, you can call release, and it will go from unscheduled to finalize, which will schedule the contract. However, instead of running the primary work contract in the center, it will asynchronously run a finalize and clean up for you if you assign a finalize routine. And then the contract is destroyed. This represents the repeatable execution states for a work contract. You start idle, which is unscheduled. You call schedule. The contract will get positioned inside of the signal tree as pending execution. Then it'll get executed asynchronously by some worker thread. Then it will deschedule and go back to idle and wait for you to decide you want to schedule it again. And this is the path for the finalization. If you assign a one-shot finalization, you go from idle, you call release, which is saying I don't want this contract anymore. It will reschedule itself again, but this time instead of executing the work contract in the middle, it'll execute the finalize routine that you've assigned when you created the contract, and then it will clean up. So I've got short on time, so I'm going to just skip over the review of what I've just told you, except for the end. So when you schedule a work contract, it puts a signal into the underlying signal tree. But there's a scheduling coalescence here. So you could have many different threads scheduling the same contract. It'll only get scheduled once. So the system is designed so flexibly that multiple components can say, well, I want this to go off. And there's no synchronization. They'll all just schedule the same contract at the same time with no extra overhead at all. That turns out to be very useful in these designs. I've already covered the finalization, but it's deterministic. You assign it, you know it's going to go off at the end. And there's self-scheduling execution, which I put very useful in there for a reason. We're going to see how that works. This really cleans up architectures very well. It helps you to encapsulate your logic into your contract and not have disparate code all over the place deciding to schedule your contract for reasons that they don't need to know. The contract has its own state inside. It can decide if it needs to be rescheduled. Okay, so what a work contract is not. It is not a future or a promise. This is exactly the opposite philosophy of how work contracts is designed. Work contracts is designed to never wait. This is a lock-free system. We don't have futures promises. We do not return computation back to somebody who's waiting for it. It never blocks. If you want to forward there's some computation in a task, you have to capture some kind of egress, stick the data in there and send it out. You don't send it back to somebody, nobody's waiting. It is not a one-shot, so you could use it that way, but you'd be misusing it. Work contracts is just logic. So you want this task to sit around for a long time and be reused again and again. Think maybe rendering a screen when you move the mouse or calling receive when a socket gets pulled. You don't want this task to be recreate it every time. This is just logic. You want it scheduled to happen, and that's it. So that is the intention of the contract itself. The second component was the scheduler. So that's here in the diagram. As I've said, this is basically just a scheduler. So the work contract group owns all of the contracts that you create within it. You can have many work contract groups if you want. You can have just one. It owns all those contracts, and it is responsible for scheduling and selecting those contracts. And again, it's based on the signal tree, so it is lock-free. You'll find that when you, for performance, when you schedule a contract, that is O of 1. So it is immediate, it's lock-free, it's wait-free. So scheduling is just like that. Selection of contracts that have been scheduled is lock-free, but not wait-free. And key properties, we've kind of discussed that. I apologize for moving faster, but I have to recover that time. What a work contract group is not. It is not a queue, as we said. It has no internal structures like queues. It does not order tasks. It keeps them all available at any given moment, and it selects which one to execute. If you need serialization, then you want to attach some kind of ingress queue to your work contract task and pull the data in that way. So if you have a number of pieces of data you want executed in a certain order, that's how you do it. But you don't expect multiple contracts to be ordered in a certain way. They don't get invoked in a certain order. They just get invoked fairly. And again, work contract groups are schedulers. They do not spawn threads. They do not create any kind of thread pools or anything like that. That is up to the application that uses the system. In a summary, I'm going to skip over the summary, but that's basically the state diagram for work contracts and how it works and its deterministic state. And the summary on the work contract group, we've already gone over. This is lock-free. It's fair selection. It doesn't use queues, and it virtually eliminates contention because it does not use queues. And it scales linearly with the number of cores, at least as many cores as I've tried. Okay, so now we go into the fundamentals, how to use a work contract. We're going to focus first on the execution path. So life for every work contract begins with the work contract group, which will own it. So first we have to create a work contract group. This is the signal tree, this is the scheduler, and I've drawn a table that kind of represents a work contract group. It has a bunch of blank spots for work contracts. They're completely unused. You create a work contract by calling group.createContract, and you pass it a callable that you want to be your primary work, that every time you schedule it, this will happen. That is, effectively, that is the contract. When I schedule you, somebody somewhere is going to execute that. You don't know who, you don't know when, but it will happen. And so here we've created a work contract that has a primary work that just dumps working to the console. The next thing we need to do is schedule it, because by design, work contracts are created in an unscheduled state. So we call schedule, and it will go through the signal tree and set the signal that's associated with that contract. And then we can call group execute the next contract. At this point, that thread, that calling thread, will go into the group. It will use the schedule tree to find whichever contract has a signal set for it, and it will execute that primary work. It'll move along that state diagram that I showed. And at this point, obviously, it prints working. It then reverts itself to an unscheduled state. And as a shortcut, if you want to create a work contract that is already scheduled, you can provide an extra argument that will say that you want it created in a scheduled state. Okay, so the fundamentals for using a work contract's release. This is that final one shot just before the contract is destroyed. Now we go back to where we were before, skipping over a few things. The work contract group is created, then we go to the group and we say we want a contract. We provide a second callable. This will be the finalization routine. So you can see that in this chart, the work contract group has created contract number 1. It assigned the work primary callable, and it also assigned the release callable, which we're just going to dump release to the console. And note, in this case, we've actually used the initialization to create this contract in a scheduled state, so it's ready to go. We call the execute next contract on the group that owns it, and it will find that this contract has been scheduled and will execute it. And it dumps working to the console because that is the primary work that you asked for. It then reverts the contract, according to that diagram, back to unscheduled. So now you've got an idle contract that is not scheduled to be executed. So we're going to call release now. And release basically says, go ahead and schedule it again, but this time I never want to see the primary work function again. The next thing I want is that finalization routine. So it's scheduled, but it is not going to invoke it directly. The finalization is asynchronous, just like the work calling is. Now we call execute next contract. Because it's been released, it will execute the finalization routine and clean up. And in this case, it's not cleaning anything, it just dumps release on the console. And then, once it's released, the contract is destroyed and the space becomes available to create a new contract. Now, one of the things that makes work contracts not tasks is the fact that they have recurring execution and they can maintain state across those invocations. So here we're going to do it again. This time we're going to use a functor as our primary work callable. So this is just a countdown object. You initialize n, and every time you invoke it, it's going to print n to the console and decrement it by 1, counting down to 0, and then we'll stop printing. So we have our work contract group. We create our contract. We add as our callable a countdown initialized to 3 in the scheduled state. Nothing new there. And this hopefully starts to look familiar, the pattern. Create the group, create the contract, and call execute next contract. This piece is new. So a work contract is considered valid so long as it has not been destroyed. Even if it's in the process of the finalization, it's valid. The moment it goes away, that handle that we've created when we say create contract will say, I'm no longer valid. So we're going to keep this while loop going and keep executing the next contract while that contract is valid. And so what do we get here? What will be the output of this? Anybody care to guess? It's going to print 3 because it was scheduled, and then we're going to wind up in an infinite loop. We're never going to exit it. Why? Because once it was executed, it goes back to the unscheduled state, and it's no longer scheduled. So the loop will just keep going, but it will never actually invoke the contract's primary work. So we can go ahead and schedule it right after we've executed it. And that's going to work up to a point, but we have 2 problems. 1, we still hit an infinite loop, and 2, we have a code smell, because we're controlling this contract external to the contract itself. And that's just ugly. That gets bad pretty quickly. So first of all, why did it go through an infinite loop? Well, because it's scheduled, but it's not released. No one called release. If no one calls release, it's not going to finalize. It's going to keep going back to the primary work. So how do we solve these? Both of these things at the same time. We use the self-scheduling aspect of work contracts. So inside of the call, both in the finalization as well as the primary work contract, you have access to the namespace this contract. And you can say schedule or you can say release. And that will, inside of the logic, reschedule that very same contract or slate it for release. So now, when we execute this functor the first time, it's going to print 3, then it's going to reschedule itself. And if the countdown has reached 0, it's going to say also just release me. So now we have all the logic contained inside of the contract itself. We've gotten rid of that code smell at the bottom. We don't have some external control manipulating the contract. We don't have to maintain the state outside. It's all encapsulated inside of the work contract itself. And now the system will work correctly. 3, 2, 1, then the contract gets destroyed because we've released it. Is valid now fails because the contract has been destroyed, and we exit the loop. Again, I'll skip over the summaries. I'll hold on to it for a second if anybody has any questions on it. Exception handling. The exciting world of exception handling, usually an afterthought. Exception handling in work contracts is done in line. There is no propagation of exceptions. As soon as it happens, you get a callback for it. How do you get a callback? Well, when I showed you the state machine that is a work contract, I lied a little bit just to keep it simple. There are 2 other state transitions you can have. When you're in work or when you're in finalize, since that's code that's not part of work contracts, it could throw. We have no control over that. So if you throw from inside of your work callback or your finalization, the exception will get propagated through if you have assigned a 3rd callback in your contract when you create it, which is an exception handler. So if you assign a 3rd callable, that is your exception handler, and it must take the exception pointer. So if you throw in your work or if you throw in your finalize and you have that defined, that exception will get forwarded to you to handle immediately at the time when the exception happens. And these are the basic rules for how it happens. So internally, when you're about to invoke the work or the finalize, it's wrapped in a try-catch. Doesn't necessarily have to be. We can detect that that functor is no accept and not have the try-catch, but that's an improvement for another day. If you have the handler assigned, you'll immediately get that exception to handle on your own after you return from that exception handler, or if you don't have that handler, that work contract state will be cleaned up. So if you were in the process of working and you threw the exception, it will unschedule and move back to the unscheduled state, and everything will be set. And if you were in the finalized state, it will go ahead and set the contract up to be destroyed and then return control to you. If you did not assign an exception handler, at that point, it's just going to rethrow the exception, and tough for you, right? Learn to handle your exceptions. So that is the system used for exception handling. Execution guarantees, I believe I already kind of mentioned this. So the work contract group itself is thread safe, it's lock-free, so you can have many, many threads calling execute work contract at the same time. They don't compete. They tend to not have any contestation on the atomic locks. They spread around, and they can pick up different scheduled tasks at the same time and go ahead and execute them in parallel. So you have parallel execution of contracts, but a specific contract in and of itself is single-threaded execution. So that's actually a very useful guarantee. So no contract will be executed by two threads at the same time. There's no synchronization or any kind of mechanism to control that. That's just the way it works. So you get single-threaded execution of your contract for free. And that's very useful because the way you usually get data into a work contract is by capturing an ingress or an egress queue. And you often want to chain contracts together, pass data in, use that contract, pass the result over through a queue to another contract, et cetera. And because it's single-threaded, often we can use lock-free, single producer, single consumer queues for that task because of its single-threaded nature. Now, in the future, I do have a design that will allow multi-threaded execution of a specific contract. I'm just not sold on the idea that it's useful at this time. So I haven't bothered to implement it yet. I'm going to skip over the overview just because of the time we lost. Okay, at this point, people are going blah, 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 I'm bored. What the hell, right? That's enough boring stuff. So we can use this system now to build something real. We've got this new toy, let's start playing with it. So I apologize because I did have a live demo set to work here, but unfortunately I had to reboot to Ubuntu, and that's not on the Ubuntu side of this machine. So we won't be able to do the live demo, but we're going to build a networking component. Now, in this group, if I call it networking, and it doesn't actually go over the wire, someone might throw one of those monochrome bottles at me, and if you're going to do that, let me know so I can duck. This is inter-process communication, but it's going to emulate multicast using multicast queues. Now, we're only going to touch the surface of multicast queues because that's beyond the scope of this particular talk. If you want to learn a lot more about the details of multicast queues and what goes into it, you should check out Jody's talk from earlier this week, although that gets scuttled by some technical difficulties. You did present that previously in Europe, I believe. So there's a much better, much more complete talk there. And you can learn much more than I can present here. We're going to build a multicast queue producer and a consumer. Then we're going to create a socket, in quotes, basically wrapping the consumer and making it look like it's a socket with the socket API. We're going to create a polar, and it's going to scale massively with work contracts, and then we're going to not show a demo. That's why I had fingers crossed in parentheses, because that's what happens. So what is a multicast queue at a high level? A multicast queue it simulates multicast over a network. You've got an allocation of memory, either in shared memory or in your process space, if you want to. And you'll have one producer, and he's going to just blast messages out into this circular buffer, this ring buffer, appending one message after another. And when he reaches the end of the buffer, he's going to turn around and start overwriting the original data again. And we can see that here. Here's the write position, he puts a message, and he puts another message, and he keeps on writing until he gets to the point where he can't fit any more data. So he circles around to the beginning and starts overwriting the messages again. which destroys the original message. So this, in a lot of ways, emulates multicast data. If you don't pay attention and aren't quick enough to get your datagram, tough on you. You've lost your data. The same thing here. If a consumer listening to this ring buffer cannot parse those messages before the writer turns around and overwrites it, you've lost your messages. So it's urgent that our consumers can ingest that data very, very quickly and keep up with the pace of the writer. Things to notice, there's no write address. No read address, just a write address. Why is that? Well, if we had a read address associated with that buffer, that would be a single producer, single consumer queue. We want multicast. So we want many readers to be able to access that exact same data and read at the same time. So we don't have a read address in the buffer itself, because that makes no sense. That would be just one reader. So we're going to simulate here the reader. So we've got now a reader who's looking at the exact same memory as the writer. The writer has produced 3 messages. The reader can observe, usually in the header of this buffer, where the write position is. So it knows where the writer is, it just can't manipulate it. But it has its own read pointer. And so it can start to consume the messages as the writer is pushing messages in. And the goal is to keep up with the writer or get lapped and lose data. So the writer has now stomped on the beginning of the buffer again as it's circled around, but that's not a problem because the consumer's already consumed those messages. And we go on. And as long as the read position and the reader can keep ahead, everybody's going to be happy. Now the reader has circled around because it reached the end of the buffer, and it's consuming the start of the buffer again. Now, I'm not going to go into details on the multicast producer or consumer classes themselves. This code is all available. I'll make it available right after the conference. I wrote it in a couple of hours, so it's stable, it's efficient, it's not perfect. But this is the minimal API that we'll need. The producer is just going to have basically a push function. So you give it a message to put in the queue, and it will just go and copy it into the queue. It'll take care of the other things that we're not really discussing, like sequence numbers. It'll adjust the write pointer and all of that. But this is as much as we need to know now about the producer. And here's an example of it pushing messages. I love that joke. And this is the minimal API we need for the consumer. Now, this may look like an overly complicated signature here, but it's designed because we want the consumer to be as fast as possible. The process of consuming messages requires that you access atomics under the hood and all kinds of things that you don't want to duplicate. So this signature basically says, give me a span of the buffer that you want me to put the message in, but by reference. And I'm going to adjust it down so that when you get it back, that's the message. You can give it a 2K buffer. It'll be down to 16 if it has a 16-byte message. The return is the remaining data in the queue, which is not processed by that particular consumer. So if the writer has written 20 bytes and the consumer pops off a 10-byte message, that's going to return 10, saying all in one shot, here's your message, here's how much you have left to consume. And that design basically allows us to be as efficient as possible. And you'll see that in action in a bit. So here's an example of the consumer. We have a 2K buffer. I chose to make this a 2K buffer because it's emulating multicast. Datagrams are usually less than, unless you get jumbo on, that's it. So it can't be any bigger than that. And the demo doesn't write any bigger than that anyways. So you set up a span over the buffer. You ask the consumer to pop the message. It returns the bytes that are left. If the message isn't empty, dump it to the console just to prove that we got it. And then continue on as long as there are bytes available. That's a simple example of a consumer continuing to grab messages off of this queue as the writer writes in. It's simple. There's extra details we have to worry about. We'll cover that in a moment. So what we have here is basically something like the top, the producer would blast out messages, and the consumer at the bottom does exactly what we just showed. It'll spin forever, and it will just keep trying to pop messages and keep ahead of keep close to the producer and dump those messages out. So this is basically not asynchronous, right? We can have a core dedicated to consuming whatever the writer does. But that doesn't scale well. So I work in market data. The exchanges often have many multicasts. Some exchanges have up to, I think, 96 on the Opera exchange. So we don't have 96 cores. All right, and also you might be listening to many different multicasts. So you don't want to sit there and poll all the multicasts and hope that a message shows up someplace. So we're going to need to have some kind of concurrency here, and we're going to get asynchronous behavior at the same time. The first step we're going to do is we're going to wrap that consumer that we had to make it look like a socket. So we're going to add a receive function to it like this. We're going to add two handlers, a message handler, which are basically callbacks. I know no one likes callbacks, and a loss handler. So one thing I didn't mention about the multicast consumer is that it can detect when it's been lapped, and it has a callback saying, I've just lost 5 messages, or 10, or whatever it is. So that's this extra handler here. We're going to create the socket. We're going to give a path to the shared memory so it can join the memory that the writer is writing, and the handlers so that when you get a message, you can pass the message back through that handler. And if you get lost, you can get that report back as well. And the reason we're doing the handler is because eventually we're going to want this to be asynchronous. And so you can't just return it from the receive call. And we add a receive call, which is going to basically do that consume process that we just went over. And in the private section, we're going to have our multicast consumer, which is that primitive that just goes and reads as many messages as it can, and the handlers, we put them in the private section. And these are the implementations. So the constructor basically goes ahead and constructs the consumer on the shared memory, and it retains the handlers for use. The receive does exactly what we saw before. It goes ahead and sets up an array. It spans over it. It tries to pop a message. If the message isn't empty, then it routes that message back through the message handler that was assigned. So calling receive here, if there's a message, will get routed back through the callback, which was assigned at the constructor. So previously we had what looked more like a freestanding function. And now instead at the bottom, we have a multicast socket with a path to the shared memory and the two handlers. So the first handler says, if you get a message, give it to me here. We'll just dump it to the console. And if you get lost, I'm going to report that there's been loss. And then we can go into a loop and just say multicast socket.receive. There's a problem with this. It's still not asynchronous, right? We're just sitting there polling. So how are we going to make this work? We're going to add work contracts. So every socket is going to get a reference to some work contract group that's owned higher up in the application. We're going to move the receive to the private section because we're no longer going to call it explicitly, or directly, I should say. And we're going to create a work contract that's associated with this particular multicast socket. And as we construct the socket now, we're going to accept the last parameter as the multicast group. We're going to ask it to create a work contract for us. And the primary work there will be to call this.receive. So when you schedule this work contract, this socket will try to receive a message. And if it can receive it, it will pass it back through the message handler like before. And now we can see why there's a callback, because this is going to be done by one of the tasks, one of the threads that will execute the task. Now, everybody's going to call me on this. You shouldn't capture this. Well, guess what? This is slideware. So I can do that. Also, we can make it non-copyable and non-movable. But the reason I bring it up is because it's actually safe to do that. You can capture this in your callback because the contract is going to be destroyed before the object that owns it is going to be destroyed. So you're never going to get a callback anyways. It's more dangerous to capture this in the release because the object could be gone away and the finalization is asynchronous. Now you've got a problem. However, that is solvable too, thanks to actual work contract releases. That's beyond the scope of this particular conversation, but if you check out my actual networking library that uses the same technique, there, everything is captured by this, and we don't worry about the finalization because we're actually using a pimple idiom. So we have the pointer that goes away, but the impl is actually not deleted at that time. It's deleted by the finalization routine. So it deletes itself after it's finalized and therefore can never be called again anyways. So with this, we have achieved our asynchronous behavior, right? No, we have not. Why have we not? What's gone wrong? Well, we didn't schedule anything. Again, so hooray for self-scheduling. Inside of our receive call, we're going to see that return code from POP. How much data is left in this queue after I've taken a message out? If there's data remaining, this contract is going to schedule itself again because it knows that it's going to need to come back and get more data very soon. So we don't have an outside influence deciding which sockets have data and which ones need to be rescheduled. It does it itself. This encapsulation is very nice. It contains the logic and makes for neater code. So now we have asynchronous behavior, yes? We still don't have asynchronous behavior. Why? Nobody told the socket it had data in the first place. So we need a polar. So this is also available after the talk in a GitHub repo. It's an embarrassing polar because I slapped it together in about 10 minutes, but it does the job. So every socket will get the polar in the constructor, and it will register with the polar. And the polar's job is basically just to sit there and observe all of the shared memory queues, watch the right pointer. If the right pointer moves, then it's going to call all the sockets that wanted to be associated with that multicast queue and call on select. So that will actually go back into the socket and just say work contract schedule. So it schedules that socket to start receiving again because it saw that there's data. Now, keep in mind that the schedule itself is wait-free. This is just a couple of atomic operations, non-blocking, so it's extremely fast. So the polar itself is going to go through a small list of sockets that want to listen to that stream that it just noticed the right pointer had moved on and hit them all. But these are all wait-free operations, so it's not going to block the polar at all. It's just going to go and go back to what it's doing, which is really important because if you have a real multicast situation, you want your polar going back and checking for more incoming data immediately. You don't want it blocking. And this design does that as well, only it's for multicast queue. So we keep the polar around as well because when we destroy this object, we want to deregister with the polar. We won't go into details on that, but that is why we have to have a polar. So in our main, this is what it's going to look like. We're going to create a work contract group. We're going to create a polar. Now we're going to create one of these little multicast queue sockets. We're going to give it the path to the shared memory that it's going to start reading from. We give it the handler so we can get our messages out. We give it a handler so that we know when we've lost data. We give it the reference to the work contract group that we want it to be associated with and a reference to the polar so that it can register itself. After that, we create a worker thread. This is the first time I think we've done this. So now we have an actual population 1 thread pool. And it's just going to sit there and keep calling the work contract group, execute the next contract. Just keep going. Whatever it is, keep doing it. And then the main thread is going to go and start polling the polar. Now, that's obviously a hot loop there. This is going to keep on burning the core, poll. But as we said, in the real world, and if you've got an environment where you've got deluges of packets coming in, you really do want to burn the core anyways. You want your polar never stopping and always looking for new data. This is a toy example, but we do it here as well, just for that reason. So, victory, we finally have our multicast queue socket reading thingamawhatsit, and it is working asynchronously, and all of the logic is contained in the socket, so none of this code actually manages the socket anymore. It's completely self-guided now. And it's powered by that worker thread. So what can we do with this now? Well, now that we have this set up, we can create a whole army of sockets. We just pass along the work contract group, and every one of those sockets is going to go and get its own unique contract. It's the same logic applied again to each one of them, but they're all independently guided by their own contract. So when one is scheduled, that one will get executed. If many of them are scheduled, the thread pool will go and find them all and call receive on all of them. Similarly, we can expand our thread pool to a respectable size and add a whole bunch of workers. And because the work contract group is thread safe, we can go ahead and call execute next contract with all of them. They'll go into the same contract group. They'll spread out and find different contracts, which are all sockets in this particular case, and they'll all start calling receive, and all of these sockets will start getting callbacks for messages. The main thread, again, is going to act as a polar, and then we just join all the workers on the way out the door. Now, at this point, I had a demo set up so I could show you. And I apologize, it's on the other side of the other OS, and I cannot show it to you. But I could show you a picture of it. Okay, so imagine, if you will, that this terminal was updating every second. You could see up in the corner, this particular demo, you could assign the number of threads you want to assign, and you can assign the number of readers that you'd like to see. It tells you exactly how fast the producer is producing messages, at what rate, and how much it's produced. In this particular demo, it's going up and down and peaking at about 2 million messages, not bytes, messages per second. So this is a really active producer. In finance, in market data, That's pushing what any exchange would do. You'll see bursts, I think in April when there was a lot of volatility, some of these exchanges went up to in the neighborhood of 8 to 15 million messages per second, but only for bursts of milliseconds. And then we see the aggregate number of messages that all of the receivers had received and any loss. And in this case, there was no loss. The things to take away from this very still unanimated picture is that all of these sockets have received approximately exactly the same amount of data. They have consumed pretty much exactly what the producer has put out. Now keep in mind that there's 256 of these guys. That's a lot of sockets. They're all sharing the same 4 cores. And because of the scalability of work contracts, none of them are falling behind. They're all consuming the data independently. At the same time, none of them are getting starved. Every one of them is getting serviced equally. That's why they all have roughly the same amount of messages received. No loss whatsoever. If I had the working demo, I could bump that up to 512 sockets, and we would still have no loss. You push it up to 1024 sockets, and I need to start doubling the number of threads. But it's only using 4 threads, and it's consuming more data than probably all the exchanges put out together. Maybe at highest peak, we'd have to go higher. So this basically shows us that it's super fair. There's nothing magic in the scheduler. It's just fair. Nobody's getting starved. Every one of them is keeping up with a producer that's producing at a pretty prodigious rate, 2 million messages per second, constant. And I wish I had the full demo so that I could show you it. And this is a walkthrough of the code that's in the demo. Basically, this looks exactly like what we just went through. So the demo does nothing special. It creates a poller, and it creates a thread to hit poll forever. And then it starts creating the producer, one producer. It gives it the path that it wants to use for shared memory. We create the work contract group. Just like before, we create a whole bunch of sockets, point them at the work contract group. In this case, we have a couple of freestanding functions for our callbacks, just so the GUI could update and track how many messages, et cetera. And then we just create the work thread pool at the bottom, and that just keeps calling execute next contract. And then the main thread itself gives a couple of milliseconds for all these threads to start up, so the writer doesn't have a chance to loop before the readers even start. And that's it. It just sits there and it waits. And all of the magic happens just through the work threads alone. They have no knowledge of what they're doing. They don't know they're dealing with sockets. Nobody knows what the sockets are doing. They are self-governed. They're not getting starved. They're getting treated equally. And they're consuming a prodigious rate of messages because the entire system is lock-free. There's not one mutex in the entire system. And all of the scheduling is wait-free. So I don't think this could get more efficient than it is. I wish I had the demo to prove it. So if you can't explain things simply, then you don't understand it enough. Now, I built this thing. I don't think I understand all of the nuances of it yet. I'm still learning it myself. So you build these neat little toys, you play with it, you start to discover edge cases, usage for it. This is actually in use in production in systems that I've built. So I know it scales well. But I'd like to think that there's more to discover here. I hope that I presented this simply enough so that everyone understands some of the potential of the system. And with that, if anybody has insights that they have, they can help me learn what's left to learn about this. I welcome the opportunity. And I'll leave you with my little marketing promo for work contracts. And at that point, I guess we can open it up to questions since I don't have a demo to show, if anybody has questions. Oh, I'd like to point out one more thing. I don't know if people noticed it or not, but this entire system is driven with about 15 lines of work contract code. So that much power with a handful of lines of code, personally, I think that's pretty impressive. And there's hopefully everybody's got a chance to read the public service announcement. Jody.
So, thank you very much. I've been looking forward to this talk since I saw it announced on the program schedule. And I really appreciate your time that you've put into this and the previous talks and the code on GitHub. I have a number of questions, so.
Oh boy, he's gonna punch giant holes in my.
I'll cycle back through if I need to, but so I want to make sure that I clearly understand. So part of my questions are like statements that I want you to either confirm or
Assert, yes.
Yeah. So the contracts themselves all have to be stateful because it didn't look like there was any way to pass any parameters into those functions. They're nullary called functions, right?
Well, yes, they're null. They don't accept any arguments. However, they can capture whatever they need.
Sure. Yeah. So they capture whatever state they need, can they be copyable? Is there a restriction that they just be movable, or?
They are not copyable. That would just wreak havoc in the internal systems where the schedules, the signals are all set up. And if I did that, I'd have locks and all kinds of other things. So no, it is movable, but that's it.
Right. And the way that you were describing the things that look, you've got a thread that's basically doing all the polls to make sure that things are scheduled. You've got some number of threads that are running the contracts.
Mm-hmm.
So the typical way of doing this stuff is you set up a thread and it just has a bunch of queues that it's reading off of, and it's scanning them and processing those, and you have to balance your threads. This allows you to automatically schedule them and forget about it. The problem that I see that I want you to help correct me on is that you lose cache coherency, and you can probably have cross-NUMA issues because it looked like any contract could run on any thread.
Very well
said.
said.
Is there a way to specify that these contracts I only want them to run on certain things, or can it recognize that you're using the same socket? Basically, if I've got 3 or 4 things that are all consumers off of the same multicast queue, they should probably be close together in some. So I'm just wondering how that works.
This is true, and this is one of the issues that you need to know what you're doing and how to manipulate these things. That's why you can have more than one work contract group. And it's one of the reasons why it doesn't come with a thread pool. So if you had, you were listening to, say, the Opera Exchange, I'm sure you understand how big that is, right? So you've got almost 100 multicasts coming in, and you don't want threads bouncing around all over the place, servicing everything. So you break up into different contract groups and say, okay, this one's gonna handle these 16. And I'm gonna have a thread pool that's gonna do nothing but poll or service that particular contract group. And I'm gonna pin those threads that service that contract group to this particular subset of CPUs on this NUMA node that's closest to the interface that these particular multicasts are coming in on. And then you create secondary work contract groups with other threads that service just that, pinned to other cores that maybe hit the other port and are NUMA aware on that side. And so you can run into problems, yes. But if you're managing 100 sockets, tell me how you're not going to have some kind of cache obliviousness.
Well, that's why you have to be very explicit about your planning up front.
Yes.
So your configuration has to know, this thing's going to run specifically on this core, and it tries to pair them with that. So that's why I was wondering if it was.
Yes.
But it sounds like if you are meticulous about how you set up these contract groups, that you can coordinate that.
Yes, and a lot of that can be done dynamically as well. You can run the IP table and see exactly which multicasts are coming through which port and how many multicasts it is, and assign a contract group that's big enough to handle that, and put only those multicasts on that contract group, which is going to look at as a pin to this particular NUMA node with these threads, just enough for however many sockets coming through that particular port, et cetera.
And let's say that your data is coming through through a SolarFlare, and you've got a SolarFlare ring buffer.
Mm-hmm.
Is that shareable amongst the contracts, or do you have to have one job specifically to take a copy out of the ring buffer and put it into one of these queues that's contractable?
Well, first of all, obviously you don't copy with SolarFlare. So
you're correct. That's why I'm asking how the contracts work.
The way I've designed it, in production grade, I don't want to go too far into the secret sauce of Lime itself, but I can mention that I think this. So basically, we have a number of EFVI polling interfaces, and each one is connected to a work contract group of its own with its own threads, and to the sockets that service that particular virtual interface. So yeah, we have to be aware of
work contract group thing.
Yes.
That you're doing with the SolarFlare rings thing.
Yeah, actually, I have a defined interface that has a thread pool, and it has the all the shared memory buffers, and hits exactly one EFVI virtual interface. And so you have to logically group things together, otherwise you will obliterate your cache and you will lose performance. So yes, you do have to think ahead.
Great, thank you.
You're welcome.
Thanks for the talk. I also have a couple of questions. So my first question is, so when you create a work contract in the sort of constructor, you pass in like the work, like the finalizer, and optionally the exception handler. I wanted to know what your thinking was in, as in why have a separate exception handler rather than have the work have a try catch inside it?
Well, that would be up to the person who wrote that particular contract, and so we handle it for you. Basically, the code that is about to invoke that callable will wrap it in a try catch, because I don't know what you've put in your contract. But I do know if you throw and you don't catch it, you've screwed up my state machine. So that the guard is there for that reason. As I put a little asterisk, I think, next to that slide, there is no reason to have a try catch if the callback is no accept, because it's going to terminate the app anyways. So that's one thing we can improve there. We don't have to wrap it with a try catch in that case, but there is no cost to the try catch other than maybe slightly bloated code, which could have instruction cache issues. But beyond that, it's something to do. But that's why we catch it outside.
Makes sense. And coroutines. When looking at the work contract interface, I couldn't help but think like this looks very coroutine. Like you have a coroutine type where, you know, in the constructor, in initial suspend, you create a contract, and final suspend, you delete the contract, release the contract, and then every time you have a core waiting suspend, when you resume, you just schedule the work.
Cooperative scheduling, yes.
Resume the coroutine. So have you had any thoughts about how you could integrate coroutines?
Well, it's undeniable that there's some parallel to it. The system is obviously designed to be task-based, but there is a lot of overlap in the scheduler that is very much like coroutines. So it is, while this is designed to sort of be mean and lean and you control every nuance of everything that goes into it for latency purposes, I don't see a reason why you couldn't use the signal tree itself to make a fair scheduler that could go with coroutines. So it wouldn't actually execute anything, but you could use that as a scheduler. And I've toyed with that idea because there is some overlap.
Cool. My last question. So around the end, you mentioned that you couldn't get more efficient than this, that you have and you don't use the mutex.
Right. Well, maybe you could get more efficient. I would have a hard time doing that myself. I think it's the maximum that I can achieve.
I was curious to know how the program would behave if the publisher paused for like 5 seconds and then the receivers had nothing to receive. If there's no mutex, that means the thread that's calling execute next work contracts isn't like
Excellent point. Excellent
for
point.
like something to happen.
Yes, excellent point. This is designed this way because I'm used to thinking this way. In finance, you burn the cores. You don't stop ever. And so this is designed to emulate that, to get the maximum throughput, basically to showcase work contracts. However, if you look at work contracts library, there is a blocking version. You have to create a blocking work contract tree, and it's almost as performant as the non-blocking. In fact, I mean, they could be merged together and you wouldn't notice a difference. There's a minor amount of overhead. So the non-blocking version gives you non-blocking, the blocking version gives you blocking contracts, where you can say, execute next contract in the next n number of seconds. And it will then go into an efficient waiting mode using condition variables under the hood. So, but if there's actually something ready, it never does that. It doesn't hit a mutex or a condition variable if it sees that the tree's got something in it. So it's just about as efficient. I didn't bring that up here because I don't want to expand the talk that much. But yes, there is a blocking version of it which will stop burning the cores. Excellent question. Thank you.
So I have a question about this contract schedule.
Mm-hmm.
Like I'm assuming it uses some like thread local state to figure out what's the currently active.
It's using a thread local, yes.
Yeah,
So before it calls, it sets up the thread local pointer to the internal guts of the scheduling system itself.
I've imagined that most contracts would just decide to potentially reschedule themselves at the end. So wouldn't it be easier to just return like a Boolean or something whether the contract wants to go again instead of having this magic global thingy?
Can you rephrase that? I didn't quite get the question.
Instead of having this thread local state and then you call this global function, you could just have the contract callback return an enum or something to indicate whether it wants to be rescheduled.
Originally, I had a design like that, yes, but I want work contracts to be as generic as possible, put no constraints on the people who use it.
Okay.
So having that would sort of leak work contracts into your code.
Right.
And so I opted not to do that. Plus, the second you return it, you've committed people to testing the return code, and you put branches into the code. But you may not need to because your logic may always want to reschedule. So you can avoid forcing the person who uses work contracts to adopt your return code, to have to check your return codes every single time. And also, it would think about the caller that says, go ahead and execute the next work contract. Now he has to listen for the return code, decide what it means, and now he is responsible for rescheduling the contract. Whereas if you do it from inside, it's the contract which is responsible for itself. And that's a great separation of concerns. So I did originally have a design like that, and I opted for this instead for that reason.
And I'm assuming if you just call this function outside a contract, you just get an assertion failure or something?
You get what?
If you just call this in main or something, you just get an assertion failure?
No, you can schedule from outside too. When you create the work contract, you get that handle, and that can schedule as well.
Yeah, but,
so,
like this contract function doesn't work, obviously.
Oh yes, no, yeah, it's null if you use it in the wrong place. So it's good for the life of the callback for the work and also in the finalization. Are there any other questions? All right then. Well, I thank everybody for your time and for listening. Enjoy the rest of what little is there of the conference.